Hello and welcome back to CS300 Introduction to Algorithms. And I'd like to start today's session with a brief remark regarding the pedagogical concept. Right, so in this course, we're focusing on higher levels of Bloom's taxonomy of cognitive learning. So this is a kind of classic in pedagogical theory, that the foundation of learning is knowledge. And building on knowledge is comprehension, application, analysis, synthesis, and evaluation. Now, you are undergraduate or maybe even graduate students, and I'm sure you have learned how to obtain knowledge as a elementary, middle, or high school student in your first semesters here. Therefore, I take it for granted that you know how to acquire knowledge, how to reproduce knowledge, and if you don't know something, how to look it up, for example, in the internet. So therefore, the focus on this course is on higher levels of Bloom's taxonomy, on comprehension, that means understanding, on application, analysis, maybe even synthesis, and some evaluation. And this is also reflected in the homework assignments and in the midterm and final exam. So that means yes, don't worry about memorizing the content of this lecture. Instead, focus on understanding, trying to reproduce, and occasionally I will actually recommend you to solve or to adapt some of the topics that we've discussed. And last time we had such an example. At the end, we had this quiz where you were asked to demonstrate your understanding, your comprehension, to apply the knowledge you've gained about the 5 algorithms for Fibonacci numbers that we've presented and analyzed, and to determine which one has asymptotically least bit cost. So these are all examples of climbing up this hierarchy. And I will return to that at the end of today's lecture. But let's first resume the course contents. We have talked about the recurrences and their solutions based on the master theorem. And this is one example of where we really are satisfied with knowledge, because the proof of the master theorem is provided in a different course like discrete mathematics. But also the master theorem is relevant for us as for the purpose of application, applying the master theorem in order to analyze the algorithms that we're now going to present. So let us recall the master theorem about an entire class of recurrences that are particularly well suited for divide-and-conquer algorithms, which we'll have a lot of today. And this covers the divide part and the later recombination part, whereas this covers the recursive part, A recursive calls to the same algorithm on subproblems whose size has been reduced by an integer factor of B. And depending on what is the relations between A and B to the D, the solution asymptotically grows according to these 3 cases. And the benefit of asymptotic calculus is that here we can ignore various complicated factors, constant factors, provided that A, B, and D are indeed constant. And we're going to apply this now to the problem of polynomial multiplication. And today we're going to see infinitely many algorithms actually of better and better computational cost for the problem of polynomial multiplication. So for Fibonacci numbers, we had 5 algorithms of better and better performance asymptotically. And now we have infinitely many algorithms for polynomial multiplication of better and better asymptotic performance, thus demonstrating and illustrating the importance of asymptotic efficiency. So, but let's start following our own virtue. Start with the problem specification. What is input? What is output? And which operational primitives are we allowed to use in composing the algorithm, and at what computational cost? So the input specification is the following. Input consists of 2 polynomials of degree less than n. So the leading term has order n-1. That means the input is given by n coefficients a0, a1, a2, up to an-1. That's n coefficients, univariate polynomials, and the same for a second polynomial b of degree less than n. That's the input. And our specification for the output is the coefficients of the product polynomial, a multiplied with b, product. And how, so the output is also a tuple of coefficients, vector or array. And let's record how many coefficients are we supposed or expect to output. Well, the input polynomials have at most degree n-1, then the output polynomial has to at most degree 2 times n-2, and therefore the output will consist of at most 2 times n-1 coefficients. Well, that concludes the problem specification. And regarding the operations we're allowed to use, please consider arithmetic operations, that is addition and multiplication of coefficients. And for reasons that will become clear later, we're going to distinguish multiplication of 2 coefficients from adding 2 coefficients, or from scaling a coefficient, that is multiplying a coefficient with some number, some fixed number. Only so 2 types of operation: multiplying 2 coefficients as opposed to multiplying a coefficient with some constant, or adding 2 coefficients. And the reason for that will become apparent later, because it turns out that the form is going to dominate the asymptotic cost. So we're going to put more emphasis on minimizing that number, particularly in our recursive algorithms. And if that doesn't make sense for you now, just stay tuned and watch it later unfold. So, and for convenience, we're going to decompose. The purpose of Divide&Conquer is decomposing the problem. And we're also accordingly decomposing the output into 4 parts. So the output polynomial has degree up to 2n-2, and we're writing this in 4 blocks. First consisting of the coefficients up to n/2 - 1, then the coefficients starting with degree n/2 up to degree n-1, then n up to 3/2 times n-1, and then 3/2 times n up to 2 times n-1. And again, this will turn out to be convenient in order to implicitly describe our recursive algorithms. I'm not going to use pseudocode in this entire lecture today. And yes, as I said, we're going to count the arithmetic operations, and we're distinguishing multiplications of 2 coefficients from calculating a linear combination, that is either adding 2 coefficients or scaling a coefficient, for reasons that become clear later. Scaling means, for example, multiplying coefficient by -5 or adding 2 coefficients. And now we start with the first naive algorithm that kind of is the algorithm derived from the definition of polynomial multiplication. And as you know, the kth coefficient of the product polynomial, ck, is given by the distributive law of pairwise multiplying all these. That is basically by the convolution. So here you see the convolution, non-cyclic convolution. So aj multiplied by bk minus j, and then take the sum. And converting this into an algorithm means the sum becomes a loop. And every loop consists of a multiplication and an addition. And the loop j ranging at most up to n, right, or 2n, so that this is a loop of with computational cost n, additions and multiplications. And we want, of course, every coefficient of the product polynomial. So we outside of this loop, there's another loop with k ranging from 0 to 2 times n minus 2. So it's two nested loops that are present in this implicit algorithm derived from the naively from the mathematical definition of polynomial multiplication. That is a algorithm with quadratic cost. Basically, the same algorithm with the same quadratic cost can also be obtained by spelling out what you in school have learned as long multiplication, or the approach we take here is by describing a recursive algorithm, right? We want to forcibly apply the divide and conquer paradigm. So to do that, let's split the input polynomial A and the input polynomial B into polynomials of half the degree of degree less than or equal n over 2. And so again, here we split the polynomials, also now the input polynomial, into the part of degree less than n over 2, and the part consisting of monomials of degree starting with n over 2 beyond that. So we can, from this part, we can factor the monomial n over 2, so that a1 is in turn again polynomial of degree less than n over 2. So a0 and a1 are now polynomials of degree less than n over 2, and a1 is kind of how to say shifted with this factor. And the same for b, degree less than n over 2, degree less than n over 2. And as I said, we also want to express the output polynomial in these blocks. But now here the block decomposition is a little bit skewed to that. Namely, C0 covers this part. C0 is a polynomial of degree up to n over 2. And C1 is the middle part. And C2 is this last part. And these, I have to correct myself, are now polynomials. C0, C1, and C2 are polynomials of degree less than n. Okay, so there's some overlap here. C0 covers here, C1 covers here, and C2 covers here. And the overlap is not really something that we need to worry about from the computational cost. Well, the algorithm has, of course, to take care of the overlap, but doing so means taking the sum here of this overlapping part that is present in C0 and in C1, but that's only the linear combination that incurs a linear cost. That's not what demonates asymptotically later, as you will see. And same here, there's some overlap between these parts, but we're not going to put too much emphasis on that. Instead, we simply start with a recursive algorithm induced by that decomposition following the distributive law. And it's no loss of generality to suppose that n here is indeed an even number, so that we can carelessly perform this division, such to make sure that n over 2 is again an integer. Because if n happens to be an odd number, then we can simply add another dummy term with coefficient being 0. So for convenience purpose, for efficiency purposes, that's of course, yeah, premature optimization is the root of all evil. So let's just suppose without loss of generality that n is indeed even. And then applying the distributive law, we can express C0 as the product of A0, B0. C1 is kind of the mix term, right? A0 times B1 plus A1 times B0. And this is the top term. That's just distributive law. And then, as I mentioned, putting them together, this part, C0 covers this, C2 covers this part, and C1 covers the middle part. And there's some overlap which has been taken care of in the recombination phase of a recursive algorithm, namely divide-and-conquer means here we have a multiplication of two polynomials of half the degree n over 2. Here we have two multiplications, each of polynomials involving polynomials of half the degree. And here we have another multiplication of two polynomials of half the degree. So this is perfect for divide-and-conquer. We have reduced the problem of multiplying two polynomials of degree less than n by 4 multiplications of polynomials of half the degree. So that means the computational cost analysis, according to this implicit algorithm of pseudocode here, based on the distributive law, is the following. We have 4 multiplications, 1, 2, 3, 4, each one multiplying two polynomials of degree less than n over 2. For the original problems, multiplying two polynomials of degree less than n, plus some linear overhead. The inner overhead takes care of the cost of splitting the input polynomials in this way, as well as after performing the recursive calls, recombining the parts of polynomials and taking care of these overlaps with the additions. That's a linear number of additions that's asymptotically not going to be costly, because if we now solve this recurrence using the master theorem from the previous slide, it follows that the computational cost of this recursive algorithm is quadratic. And that is much larger than the linear cost, right? So that this recursive algorithm has the same cost as the naive algorithm and has the same cost as the long multiplication that you learned in school. So no advancement here. What's the whole point? The whole point is that by designing a different recursive call, we can indeed improve the computational cost. And the only thing we need to do is save one multiplication, even if that's going to cost us more additions, because the number of additions is still going to be linear. And this is the next algorithm we're going to discuss. It's called Karatsuba multiplication, named after Russian scientist Karatsuba, who invented this, who found this during, I think, Cold War times, when it wasn't easily be accessible or to become known in the Western Hemisphere. And with that idea for this improved algorithm is to use the distributive law in a different, smarter way, namely in this way. So as you can see here, C1 is now, C0 and C2 remain unchanged, but C1 is now expressed in this seemingly more complicated form. And I encourage you to verify that this is the same expression C1 as previously here. So here was the previous expression, right? A0 times B1, A1 times B0. And now it's this complicated expression, but the benefit here is it only uses one multiplication, whereas the previous one had two multiplication. It uses more additions here, but as you see, only one multiplication. And that means that now this gives rise again to a recursive algorithm, recursive call, but on one using only 3 recursive calls corresponding to the 3 multiplications, each one multiplying polynomials of degree less than n over 2, because the sum of these polynomials, notice that there's no term x to the n over 2, so that both polynomials here have degree less than n over 2. These both have degree less than n over 2, so their sum also has degree less than n over 2, so that this is a multiplication of polynomials of degree less than n over 2. Here, same here, and same here. So only 3 multiplications of polynomials of half the degree, meaning only 3 recursive calls, and thus the improved recurrence. And from this recurrence, it's obvious that this new algorithm has less asymptotic cost, although, to be honest, the constant hidden in the big O here is now much larger, because you can see each of these additions has to be expressed by adding, these are polynomials of degree less than n over 2. So there are n over 2 additions of coefficients hidden here in this vector notation, and same here. So the constant here is significantly large, but still it's a constant. And asymptotically, what dominates the computational cost is the multiplication part here. So if we solve this recurrence using the master theorem, the computational cost is not going to be quadratic, but it's going to be subquadratic. And I want you to practice applying the master theorem and solve the recurrence by yourself. So that's the challenge for you as a kind of homework, as a practice part. Solve the recurrence for Karatsuba's law in order to analyze Karatsuba's algorithm, improved algorithm for polynomial multiplication. Now, is this the end of the story? Remember our paradigm, our virtue of computer science, design an algorithm, and we've already designed 2 algorithms for the polynomial multiplication problem. Analyze them, and we've just analyzed both of them. The first one with quadratic cost, the second one with subquadratic cost. And then check whether this algorithm is optimal. Well, the first one obviously was not. The second one, Karatsuba, also turns out to not be optimal. So we do start over again, devise a new algorithm, an improved one. And how can we generalize Karatsuba's algorithm? Maybe based on the divide-and-conquer paradigm, let's, instead of dividing the input polynomials into 2 parts, how about we divide them into 3 parts? That seems natural, and indeed so natural that Toom came up with this improved idea and devised what is now known and famous as Toom's algorithm. So this is, again, without pseudocode, implicitly based on the mathematical description, decompose the first polynomial a into 3 parts, such that each part has degree less than n over 3 now. This has degree less than n over 3, comprising the coefficients starting with index n over 3 up to 2n over 3 minus 1. And the same here, the polynomial of degree less than n over 3, comprising of the coefficients starting with 2n over 3 up to n. And same for the 3 parts subdivided into 3 parts with degree less than n over 3. And naively expressing this multiplication using the distributive law results in a recursive algorithm that uses 9 multiplication, each a0, a1, a2, with each b0, b1, b2, 9 multiplications of polynomials of degree n over 3, which results in the same asymptotic quadratic cost according to the master theorem. And here we can and will suppose without loss of generality that n is divisible by 3. Otherwise, we just add 2 dummy terms, 1 or 2 dummy terms to make it divisible by 3, which asymptotically doesn't really affect the asymptotic cost. And notationally, we also write and decompose the output polynomial into blocks of degree n over 3, again, being well aware that there will be some overlap, larger overlap, but this overlap will always be covered by a linear term in the decomposition and in the recombination phase of the divide-and-conquer algorithm that now follows from this decomposition. And as I said, the naive distributive law gives rise to an algorithm which is no improvement over the previous ones. Instead, consider the following implicit algorithm induced by the just mathematical formulas. Yes, to thus again emphasizing that efficient algorithms usually are heavily based on mathematical insights and exceed the just mere realm of coding or hacking. So here you see many equations. Here you see, for example, C0 is indeed multiply A0 by B0, gives the least degree term, and multiplying the upper degree terms A2 by B2 gives rise to C4. But the intermediate terms, well, for example, C1 is A0 times B1 plus A1 times B0. But as we already seen with Karatsuba, there's maybe a more efficient, well, more complicated way of expressing that, but using less multiplications. Indeed, here's a complicated expression for this C1. And here's another complicated expression for C2 and a more complicated expression for CC3. And I recommend you verify that this indeed gives the same correct expression for C1, like the one that we would expect from A0 times B1 plus A1 times B0. Please verify this by yourself using manual calculation. This is really provides great insights. And I see a question in the chat about where the constants comes from, and that's an awesome question that I will explain later in this today's lecture. So please stay tuned with your very good question. And another question is, what is T1, T2, T3? This is indeed, I should tell you right now. Namely, here you see the expressions for T1, T2, and T3. And right, based on these expressions, please verify yourself manually that this gives the right expressions. The emphasis now here is that T1, again, can be calculated using only one multiplication, meaning one recursive calls to the same algorithm again, now involving polynomials of degree less than n over 3. Right? A1 is a polynomial of degree less than n over 3, A1 and A2. And the scaling, remember the scaling can be written as either as repeated addition or just as scaling. The scaling and the addition part incur linear cost. So that's covered by this big O of n, and that is going to be dominated by the other part as anyway. So we don't really need to worry about computational cost. This is again an insight that only can be achieved from this higher level abstract perspective of algorithm design and focus on analysis, asymptotic cost. When I was coding myself, I had never even imagined such an approach to make sense. But as Donald Knuth kept emphasizing, premature optimization is the root of all evil. And yes, there's a question. Right. This number here means 3 plus n, 3 plus 1/2. So this is the same as our abbreviation for 7 over 2. So 7 over 2 here, 7 over 2, yes. Again, there's a question in the chat. What is the logic behind these terms? And this is the same question asked before. How did Toom arrive at all these strange numbers? Right? This looks like a miracle, like a magic, right? So strange numbers popping up, and suddenly one can get away with, that's essence, with 5 multiplications, right? These two we still have, right? But now instead of here having to perform 2 multiplications for C1, 2 multiplications for C2, right? So C2 naively would be, no, it would actually be 3 multiplications. A0 times B2 plus A1 times B1 plus A2 times B2. So the naive distributive law would give rise to a recursive algorithm incurring 1 multiplication here, 1 multiplication here, 2 multiplications here, 2 multiplications here, and 3 multiplications here, making a total of 9 multiplications, 9 recursive calls, and thus the naive recursive algorithm would have the recurrence T of n equals 9 times T of n over 3. And if you solve that using the master theorem, you're back to quadratic algorithm and no improvement, right? But using the Toom's equalities, which you can and are asked to easily verify at home, we can get away with 1, 2, 3, 4, 5 multiplications instead of 9. 5 multiplications, each involving polynomials of degree less than n over 3, rather than n over 2 as in Karatsuba. So that now this algorithm, implicit algorithm, has the following computational cost recurrence. Right here you see the multiplications involved. 5 recursive calls to multiply polynomials of degree less than n over 3 at the expense of a considerable increase in the constant hidden here. And here there are many more additions. You see, this is even more involved than Karatsuba's law. But again, asymptotically, this linear term is not the one that we need to worry about. We need to worry about this one because this gives rise to the superlinear computational cost. And again, I'd like to ask you to apply the master theorem in order to solve that recurrence and see that it's asymptotically even more beneficial than Karatsuba's law. Right, and to emphasize again, this terminology means that 3 divides n, n is divisible by 3, 3 is a divisor of 3, which we can assume without loss of generality, otherwise just add 1 or 2 more dummy terms just to make it a n multiple of 3. Okay, so that's our third algorithm. And yes, the question in the chat is exactly the question that I'd like you actually to answer. The question in the chat asks, which one is asymptotically better, Karatsuba or Toom? And yes, indeed, yes, here we have a larger number of recursive calls, but to fewer, with polynomials of less degree. So that's a great question, but I would like to ask you to answer that question by applying the master theorem about recurrences to see what is the asymptotic cost, and hint that may or may not become a quiz question later. Hint, hint, nudge, nudge. Okay, that's already our third algorithm, but I've promised you infinitely many algorithms. Where are the other ones, and how are we going to fit the remaining infinitely minus 3 many algorithms into the remaining time that we have allotted here? And the answer is given in the PhD thesis of Stephen Cook, the famous Turing Award winner, NP completeness. In his PhD thesis, he indeed generalized Toom, and yes, that also happens to be the question in the chat. Yeah, unfortunately, it's a great question, a great idea. Generalize Karatsuba, generalize Toom to larger numbers, but unfortunately, this idea is so great that Stephen Cook had it before you. So you're walking in the shoes, in the steps of giants. So please continue walking. That's a great direction. And we're going to answer this very question. Indeed, one can apply this idea to finding an entire sequence of algorithms by dividing the original polynomials into smaller and smaller subpolynomials and applying the algorithm recursively. But the purpose of the goal is now to use as few recursive calls as possible involving these polynomials of smaller degree. So let's do this. And here you see the input polynomial A now decomposed into small n polynomials. And we want to be general as possible. So we lift the condition that both input polynomials have the same degree, which actually was of no loss of generality so far. We could always pad with dummy coefficient 0 without affecting the asymptotic cost. But here, let's suppose that the first polynomial A has degree less than n, capital N, and the second polynomial B has degree less than m, capital M. And we're going to divide the first polynomial into small n blocks, small n blocks of degree less than capital N divided by small n each. And we're going to divide the second polynomial B into small n blocks, each one polynomial of degree less than capital M over small m. So now we have all these blocks. And we want to multiply the polynomial. If we do that naively using distributive law, then we would again return and result and end up with a quadratic algorithm, each term by each term. Then we're quadratic. But we want to generalize Karatsuba and Toom, who all got away with less than a quadratic number of or general here, it would be small n times small m recursive calls in total, right? Small n times small m, because we have n blocks here and m blocks here. But we want to do better. How do we do better, and how do we come up with all these strange coefficients that occurred in Toom's algorithm? So to see this, here's again what I already said orally, the terminology. First polynomial of degree less than n, second polynomial of degree less than m, and question specification, output the polynomials of the product polynomial whose degree is strictly less than n plus m minus 1, so it's at most n plus m minus 2, and we're going to abbreviate that with k, so that's kind of the output size. And right, we initially our first algorithm that we talked about was long multiplication. N times m products in this generalized setting would incur n times n products and as many linear combinations, additions, and scaling. And we want to generalize that now. And in order to generalize this, let's write this polynomial multiplication problem in vector and matrix form using the terminology from linear algebra that you're all aware of. So what you see here is a complicated way of evaluating a polynomial. So let's suppose we already know the coefficients of the product polynomial, of the output polynomial. Let's suppose that, and then we're going to determine conditions for these coefficients that allow us then to determine them, okay? So this is sometimes called an ansatz, right? So how can we evaluate this output polynomial at some argument x? Here's a way of expressing that using row vector times the column vector, which is also called sometimes called an inner product, namely 1 times C0, x times C1, x squared times C2, and so on. So you see in this terminology, this is exactly the value of the polynomial C, whose coefficients we are looking for. We're looking for that vector, right? Okay. So this is seems artificial. The row vector times column vector notation. And on the other hand, C is the product polynomial. So the value of this product is simply the value of the two polynomials multiplied. But how the subtle but important difference here we talk about values. This is not the product of two polynomials, but this is the product of two values. Let me explain that in a little bit further. So one way is to first take the two polynomials as coefficient vector, multiply the two polynomials to receive the resulting coefficient vector. This is the problem we want to solve. If and once we have the resulting coefficient vector, then we can evaluate that polynomial by plugging in, by replacing the symbolic variable x with the actual values small x. Or the approach we take here is first evaluate the two input polynomials at some variable, at some argument x, where x now divides argument and not a variable anymore. Similarly evaluate the polynomial b at some value, same value x, which is again now not a variable anymore, but a value, and then multiply these two values to obtain the value of the product polynomial. But from this value, we cannot recover the coefficients of the polynomial, right? So just knowing one value of the polynomial does not allow to recover the coefficients of the polynomial. How many values do we need to know in order to recover the coefficients? Well, the polynomial has degree at most k. So k plus 1 values allow to recover the polynomial's coefficient. Theoretically, according to the fundamental theorem of algebra, any polynomial of degree k is uniquely determined by its values on k plus 1 different arguments. So here this is just one argument x. So let's do the same again with another argument y and with another argument z and so on. Let's do the same. And I'm still just talking mathematics. No algorithm has emerged so far here. So we're doing the same for many different x's, actually for k plus 1 different x's, which we can be arbitrarily fixed, right? We just need different values of x in order to be able to recover the coefficients from the values of the polynomial uniquely. So here we have k plus 1 such values, arbitrary but fixed and distinct. And we do the same repeatedly, and that's what you see here. So the first value, that's what we had before, but now we have another argument at which we do the same procedure, x1 raised to the powers, and another one, and so on up to capital K. That should actually run up to capital K, not to small k. Okay, that's the right-hand side. And now you see this has become a matrix. Here it was a row vector, and now it's a k plus 1 times k plus 1 matrix. So that the left-hand side is also a k plus 1 dimensional vector with a product value of the first two values multiplied, second values, and so on up to capital K. Should be a capital K here. And now you see that we've formulated the same original problem as a problem in linear algebra. Here is a k plus 1 dimensional vector. Here's a k plus 1 times k plus 1, so a square matrix. And here's a k plus 1 dimensional vector. And this is actually the vector we're interested in. This is the one we want to calculate, right? We want to determine the coefficients of the product polynomial. What we can calculate is the left-hand side, right? We can evaluate the first polynomial at x0. We can evaluate the second polynomial at x0. And the computational cost for this evaluation, remember this evaluation is kind of only involves linear combination. Yes, there's a question in the chat, but we'll have to postpone that and return that after describing. It's a great question, but we first finish discussing the algorithm. So evaluating this here only involves linear combination because x0 is a fixed number, let's say 15 or 12. And same here. So evaluating b of x0 only because linear combination and the lesson we've learned from all the previous algorithms is don't worry about the linear combination. This is not going to be the costly part of the algorithm. Then after all this linear combination, there's going to be one multiplication that is a real multiplication, not scaling with some constants here, but a real multiplication where both left and right hand side are something that actually depends on the input coefficients. Whereas multiplying with like 15, if x0 is 15, there is not something that depends on the input. So that this vector here, evaluating this vector, it's a k plus one dimensional vector, incurs only k plus one, that is n plus m, many products here, and many linear combinations. I'm not going to even say how many, it's a lot, but we don't care. So the left-hand side vector we can evaluate, calculate with cheaply. What we're interested in is this vector, but there's this matrix, right? And this matrix is also observed that all the numbers in this matrix are constants, right? We're going to fix that. So this is like 15, 15 squared, 15 cubed, and so on. And let's say for x1, we choose 3, 3, 9, 27, and so on. So we just need to fix distinct integers here. And then this is a large matrix, but all with integers, constants. And so this is kind of for free, and we can hard code this matrix in our algorithm that we're going to describe in a minute. We're still only talking about mathematics, ways of expressing the quantities that we're interested in mathematically, and then the algorithm will follow from that. Right, so here we have reformulated our problem as in using linear algebra. Linear algebra, I cannot emphasize enough how important linear algebra is. And in particular, some of you may have seen such a matrix in linear algebra. This is a very famous type of matrix, and it's called a Vandermonde matrix. Vandermonde matrix has each row consisting of powers of the same number. So this is a zeroth power, first power, second power, kth power of x0. Here, the second row is also same powers, but of a different number, and so on. So this is so-called Vandermonde matrix. And one particular great property of Vandermonde matrix is that they're invertible, provided that these numbers are all distinct, which they are. That's how we chose them. Let's say all distinct integers. You could even choose 0, 1, 2, 3, 4, and up to k integers. Anything is fine. Each such choice will result in a different algorithm, but the computational cost of that algorithm will be the same. But we're getting to the algorithm still. Please be patient. And by the way, on a short notice, what constitutes a great scientific talk? A great scientific talk is the first third should be understandable to everybody. The middle third should be understandable to the experts, and the last third should be understandable only to the speaker. So building up the level of difficulty. And that's also how the chapters in this course CS300 are designed, deliberately designed, ramping up the complexity, not computational complexity, but the difficulty of understanding. So if you feel you're getting lost, that's because we're reaching really one of the pinnacles of this chapter 1 on computational problems and algorithmic solution. Please bear with me. It will all make sense once we come to the conclusion of this chapter. So patience and is really recommended here. So that being said, we have now reformulated our problem. We want to calculate these numbers, these coefficients. we formulated this as a problem in linear algebra, where the left-hand side is a vector that we can easily devise an algorithm for. That is a very cheap one in terms of only the number of products. Namely, it uses only k+1 products, k+1 being n plus m minus 1, as opposed to the naive algorithm which uses n times m. So you already see here considerable improvement over the number of multiplications, which, as I keep promising, but still need to show you, is going to dominate the asymptotic cost. So n times m products here improved to n plus m minus 1 products, but then we have not recovered the coefficients yet because there's this matrix, but this matrix, fundamental matrix, is guaranteed to be invertible. So let's just mathematically, not algorithmically, multiply both sides from the left with this inverse of this matrix. Thus this matrix will vanish, and instead the inverse arises here. And this is what happens here, right? So here we have the inverse of the Vandermonde matrix multiplied by the vector we can calculate cheaply. And this gives results in the coefficient vector that we're actually interested in. So just mathematics using Vandermonde matrix. And now we recover from that an actual algorithm for calculating these numbers. What does the algorithm look like? First, the algorithm has hard-coded this in the inverse of this Vandermonde matrix. So inverting this Vandermonde matrix is maybe complicated, but this is not the purpose of our algorithm, because remember that we have n and m, and therefore also capital K, and therefore also these coefficients fixed, hard-coded into the algorithm. And therefore we can, in a sometimes preprocessing, or it's the duty of the programmer to calculate the coefficients of this inverse Vandermonde matrix, and then hard code all these coefficients into an algorithm. And what does this algorithm then do? It calculates, evaluates the first polynomial on x0, x1, and so on up to xk. It calculates, evaluates the second polynomial on x0, x1 up to xk. All these incur no multiplications at all, only linear combination, because these numbers are constant. And then perform the k multiplications here. And then perform another set of linear combinations, because these are all constants again. They do not depend on the a coefficient vector nor on the b coefficient vector. And then recover this coefficient vector of the resulting polynomial. So now we're already almost at the goal. Yes, so one great question in the chat is, what is the computational cost of inverting a matrix? That's an excellent question. That's a deep research question. But this question, fortunately, is irrelevant to us, because the computational cost of calculating the inverse is something, or the task is something that we charge the programmer with doing. And once the programmer has finished and calculated all this, the programmer will enter all these coefficients of the inverse matrix into the algorithm we're just designing. And thus the algorithm will not need to do that, because n and m are fixed. The algorithm will receive as input only the coefficient vector, not n and m. That's a subtle but important part. N and m are for now fixed, and we're devising an algorithm for multiplying a degree n polynomial to a degree m polynomial. And this algorithm will receive as input only the a coefficient vector and the b coefficient vector, but not n and not m, because n and m are fixed. And when n and m are different, we're devising a different algorithm that receives as input a different coefficient vector of different length, coefficient vector of different length, and output a coefficient vector of different length. But for every n and m, we're going to devise a different hand-optimized tailored algorithm. That's answers the question. The questions are very relevant, and really appreciate all this this discussion. Thank you very much for that. Okay, so but to resume, we're really almost there. You see the algorithm, right? It's very implicit, no pseudocode here. It's really an algorithm based on that. All this is hard-coded. Then the algorithm will perform this evaluation and then make the multiplications. And the final step is to apply this algorithm not with k equal to n plus m minus 2. Then there would be no recursive call left, right? Instead, to decompose the polynomials as described here. So now we choose for k not n plus m minus 1, but instead, right, so then this algorithm without recursive calls has k plus 1 products here and a lot of linear combinations, quadratically many linear combinations, namely here. This is a quadratic matrix multiplied to this all these coefficients. But as long as k is a constant, this part is just linear, and this is going to cost. And now we, the final step is to convert this into a recursive algorithm, namely to apply the same algorithm here, but now to the blocks, so that a here is not just the a of x0 is not a number, but a of x0 is the first block here, and the second block, and so on. So, and here's the number of blocks. So k is now not the n plus m minus 1 with capital M. Then there would be no recursive call, but instead k is small n plus small m minus 1, where small n denotes the number of blocks in which we divide the first polynomial, small m denotes the number of blocks into which we divide the second polynomial, and then perform all these recursive calls in order for the multiplication of these polynomials of degree capital N divided by small n and capital M divided by small m, plus the division, the subdivision, and the recombination phase, which costs really a lot quadratically, but as long as n and m are constants, this is the constant we're going to drop, right? So, and now I leave it to you to solve this more complicated recurrence. Well, you cannot because you don't know the values of n and m, but the point here is you can get to choose, you as programmer, you get to choose these numbers. You can choose them arbitrarily as long as they are constant. That's important. Consider, for example, that small n is equal to 2 and small m is also equal to 2, right? That means we subdivide our initial polynomials, each one into 2 subpolynomials of half the degree. Well, we had an algorithm doing that. That algorithm was called Karatsuba. Now, what does our Toom Cook family of algorithms, right? It's a family because we can choose n, small n, and small m arbitrarily, and each choice of small n and small m gives rise to a different algorithm, right? But let's just consider the case that small n is 2 and small m is also 2. Then we have 2 plus 2 minus 1. That means 3 recursive calls to multiply polynomials of degree half the degree, right? Small n is 2, half the degree. Small m is 2, half the degree. Plus something linear in n plus m. This is a constant. This is like 4 squared. So 16, but it's a constant. So that we really recover here the recurrence for the computational cost of Karatsuba's algorithm. Indeed, this is Karatsuba's algorithm when small n and small m is equal to 2. Let's do the same game again, now with n equal to 3 and m also equal to 3, small n and small m. When small n and small m is 3, then what do we get? 3 plus 3 minus 1, that's 5, right? 5 recursive calls to multiply polynomials of 1/3 the degree. This is, as you recall, Toom's algorithm. And now you see also where all the strange numbers come from in Karatsuba and Toom. They come from the pre-calculated and hard-coded inverse of this Vandermonde matrix for arbitrary but fixed numbers here. So Karatsuba chose certain numbers here. I think -2, -1, 0, 1, 2, 3, 5 numbers he would need, right? K is equal to small n plus small m minus 1. And if you calculate the inverse Vandermonde matrix for these entries, you recover, you see these strange numbers in Toom's algorithm. But now, due to Cook, we can generalize that. We can choose other constants, and we can choose other parameters, small n and small m, and obtain better and better, asymptotically better algorithms. Right. Yes, the question here raised in the chat is, how can we apply the master theorem to the bivariate case? And the answer is, we cannot. This goes beyond the statement of the classical, the naive, the standard master theorem. But when n, capital N, is equal to capital M, then the bivariate case does boil down to the univariate case, and then you can apply the master theorem and see that indeed Cook's algorithm recovers Karatsuba's algorithm, recovers Toom's algorithm, and generalize that into an entire infinite family of algorithms of better and better asymptotic cost. And as small n and small m are chosen constant, that's always important, but arbitrary, large, the computational cost of Toom-Cook's family of algorithms goes gradually towards linear. So the cost is n to the 1 plus epsilon. For any small epsilon, you can find such constants n plus m. The disadvantages, one disadvantage is of course that the constant that we keep hiding in the big asymptotic big O notation here keeps blowing up, and thus it becomes less and less justified to drop this constant, right? Another problem indeed that you already raised is the pre-processing. The programmer to set up the algorithm, setting up the algorithm becomes more and more costly. So that's two parts, kind of first designing the algorithm. We're just proving that such an algorithm exists, right? But actually devising the algorithm, spelling it out, determining all the constants becomes increasingly costly. And that cost hopefully gets amortized in the execution of the thus improved algorithm. Okay, so that concludes, that summarizes our very complicated discussion of a family of algorithms with better and better asymptotic cost for multiplying polynomials. I must also say that remember our specification that we only count the number of arithmetic operations, and here specifically we chose to focus on the number of multiplications because the number of additions and scalar multiplications are asymptotically not dominant, but the numerical behavior of all these algorithms is not good. Let me put it in that way. So when implementing this, for example, in floating point arithmetic, the algorithm behave worse and worse. But if the polynomials to be multiplied are actually integer polynomials, then not real polynomials, not floating point polynomials, then this is actually maybe a good idea. Okay, so yes, let me see how we're doing in terms of time. Right, and also let me have a look at some of the questions channel. Yes, How do we choose the numbers x0 up to xk? That's a great question. And this is something that determines, for example, the numerical stability. But as long as we only count the number of operations, this does not really matter. Another great comment in the channel says that this looks like cheating. And in a sense, it does, right? So, but let me pinpoint where the cheating actually happens, right? So in my concurrent course, Theory of Computation, I keep emphasizing that when we want to show that something is computable or efficiently computable, we need to design to show that an algorithm exists. We're not asked to actually present the algorithm, just so that an algorithm exists. And that's what we did here as well, right? I have not really shown you the algorithm, but I did show that an algorithm exists for every single choice of n and m. Why didn't I show you the actual algorithm? Because the actual algorithm involves all these entries of the inverse Vandermonde matrix. And I didn't tell you how to find them. Well, you know how to find them, but it's, of course, costly to find them, right? So the precise statement of Toom algorithm is, to every capital N and capital M, there exists an algorithm. How to find that algorithm is another matter. I've shown you how to do that, but doing that efficiently is a separate question. So the algorithm is efficient, but finding the algorithm is maybe not so efficient. You see that subtle difference? This is maybe similar to other areas in computer science where this is something called a pre-processing phase. So you get some information, some partial information, and then you can pre-process it into a partial algorithm. And then comes the rest of the information, and then the algorithm should be maybe deal with that as fast as possible. And that's what we have here. The first partial information is capital N and capital M. Then you take the time to set up a highly optimized algorithm, spend lots of effort, write that algorithm, and then comes the data, namely the n-tuple coefficient vector here, the m-tuple coefficient vector here, and then the algorithm will deal with that very efficiently. I hope that illustrates why it's maybe not entirely like cheating, but I do understand why this is maybe considered as questionable. But that's all point of problem specification. Problem specification, and maybe it's better to emphasize that, is the input is the coefficient vector. The input is not n and not m. N and m are fixed. That's, I guess, the important but subtle difference that explains why this is considered an efficient algorithm. Okay. Right, and now we've also answered the important question in Toom's algorithm and in Karatsuba's algorithm, where all these strange magical numbers come from. These strange natural numbers are indeed the coefficients of the inverse Vandermonde matrix. Okay, so yeah, time is almost up. So let me summarize. So today we saw a sequence, an infinite sequence of algorithms for the polynomial multiplication problem, which we have taken great care of making formal specification and which operations we are allowed to use. I mean, multiplications and linear combinations. That means scaling by some constant and addition. And this is an illustration of this paradigm, which is sometimes called algorithm engineering. Devise algorithm, analyze algorithm, prove optimal. If it's not optimal, start over, devise a better algorithm, analyze a better algorithm, prove optimal, still not optimal. So that we have kind of a meta loop in the algorithm design paradigm. Good, and yes, also this is a great illustration of the gospel that I keep emphasizing, that behind every efficient algorithm, there's great mathematics, sometimes deep mathematics. Here, we got away with basic linear algebra. So if you haven't, then please feel encouraged to brush up your background in linear algebra regarding Vandermonde matrix and matrix vector multiplication. So that's all for today. And I'm going to stay online and answer your questions during the remaining 5 minutes. Thank you.